share your solution. I'll make you a, okay.
Just give me a second. I gotta load it up.
Okay. While Joel's getting ready, I have not glanced at the exams yet. I had a couple come in before this morning, and then there was a flurry of them this morning. So I haven't had a chance to look at them yet. I had asked you, at least I thought I asked you to put how long it had taken you on the exam, not just, in other words, if you did it and then you went back and checked it and rechecked it. I'm just talking about the basic time to do it. Because my guess is it would have taken you 5 to 7 hours if you've been up to speed. So I'll be interested in seeing how much time you devoted to that exam, to the turkey leg exam. Okay. 8 to 10 isn't bad. Again, you have as much time as you wanted to. If you wanted to go back and recheck things. Historically, I think when people do this one, they do the K-infinity and then the buckling, and then they sort of stop and get their breath, and then they go back and do the rest of the exam. Joel, how you doing?
Okay, I'm ready now.
Okay.
Okay, my bad. So for reactor theory, can you guys see this?
I can see it.
Okay. Okay, my bad. So we had the groups for, this was U233, and we had the group. The first group was the, oh, I forgot the name, but it was 10 to the minus 8 seconds. The prompt group. This was the prompt group. 10 to the minus 8 seconds, and the total percent of neutrons from here was 99.359%. And then I had to find BI, LMI for this one. So I just basically, all you have to do is multiply 10 to the minus 8 seconds times the percent, and you're gonna get BI, LMI. And I did that for all of them. Then if I want to find L bar, I have to divide BI, LMI, or the addition from all groups from 0 through 6 of BI, LMI divided by the addition of all the groups from BI right here. And for that, I got 0.03915 seconds for the whole. That's for the whole process to to go through, including the prompt neutrons. And if you just want to find L bar just for the delayed neutrons, you have to do the same process, but just add in the delayed neutrons 1 through 6. So I did that, and the prompt neutrons didn't really make a change for BI LMI because it was like the same value, because this value is so small. So then when I divided it by the sum of all the BI, which is 0.264, which was also given to us, it was 14.826 seconds for this process to happen. I don't know if I did it right, but
Did you do the extra credit?
no, I didn't do the extra credit.
Okay. You want to scroll back down so I can look at your screen?
Oh, my what?
Okay. I got different values than you. Does anybody else have different values that they would like to share? If not, it's probably easier for me to put my solution up on the board.
Well, I have a different value for BI LMI for the prompt group.
Yep.
I got 0.09936.
That's correct.
But I'm going to be honest about this. I was only able to do that through the use of the book. So I would like, if you could show us what the math is, that would be good.
Is this tie?
Oh, because I don't know.
I'm not sure who was talking there. Was that you, Ty?
Yeah, it was him.
Yes.
Okay.
And so
Is it because it was a -8?
So what did you get for your L bar answer? Ty.
my L bar answer was 0.05769 seconds.
That's correct. And what'd you get for the delayed L bar?
I got 21.394.
That's correct also. You want to share yours or I'll just put mine up?
I can try to share, sure.
All right. So I will undo Joel.
Video. I just gotta figure out where to share screen is. This is the first time I've done this. Does anyone have any insight for me as to where the share content?
Yeah. There you go.
Okay, can everyone see that now?
Yes, I can.
Yep.
Okay. Okay, so the extra credit. So we have flux equals flux sub naught times E time divided by the reactivity. So we had given that flux naught was 8 times 10 to the minus 14 neutrons centimeters squared per second. That time was 120 seconds, and that flux was 3.6 times 10 to the 10 neutron centimeters squared. So what I did is I input that calculation into my calculator, solved for T to get negative 11.989 seconds.
That's correct. And you know it's a minus because the flux has decreased over that time span. So the period has to be minus, and that is the correct answer. You want to go back up and share the basic part of the quiz.
Right. So again, I'm not sure how the math worked out for me very simply by dividing 1 through 6, the non-prompt group. But if I divided 9.359 by 10 to the minus 3, which was the half-life, I kept coming up with a large number. But looking back at the table on page 303, I noticed that our percentage of 99.359% for the prompt group was the same as the percentage for the prompt group on uranium-235, and that led to the answer we see in column 3 on the following page of 0.09936. And I used that number. So that's where my question is where did I screw up the math? So I couldn't do it mathematically. Stop sharing.
It was a little bit misleading in the textbook on page, let me take Ty back out.
Yep.
Okay. It was a little bit misleading from the table that you had on page 303 for table 10.2 when they talked about the half-life, because when these prompt neutrons are born, remember, they really last about 10 to the minus 14 seconds. That value that they put in there, 10 to the minus 8, is not really a good number, because the real number you're looking at is the amount that it's taking to slow down, which is around 10 to the minus 3, 10 to the minus 4. And this is for all fissionable materials. And I was hoping that you were going to go and follow the example 3 on the next page, 304. And you noticed for the 0th group, which was the prompt group, that the LMI value was 10 to the minus 3. And 10 to the minus 3 is really the slowing down time for that particular neutrons in that particular isotope. So whenever you're working any type of fissionable fuel and you're looking at that LMI value, you should use 10 to the minus 3 for any fuel. So if it's uranium, plutonium, thorium, whatever it is, notice they put an approximate, so that's a good number to use. When you did the rest of that, and I'm just going to throw up a couple of these for me. So I usually just set up a table sort of like they did in the sample. We have the prompt group, and then we have the 6 delay groups. You have to account for everything. This one I would just leave blank, because again, it's that time that it takes to fission. So then I put in the others, and these are all in seconds for this particular fuel. Then I put in the B sub i's, and then this is the percent of total neutrons. Again, this was from the table. And then for the L sub mi, this is about 10 to the minus 3. And then for the others, you take this number, you divide by 0.693. So you're going to do that in every case. And then you're going to take this number, multiply it times that number to get this value. And so I had and then I added all of these up, and I came up with 5.7474. The sum of all these B's is going to be 100, because you know it has to total up to 100. The actual sum, if we look at just the delay group, which is 1 to 6, that value was 0.264. So I'm going to erase this. So if we take this total divided by the total number, that is L bar, and that value was 0.0575 seconds. So you can see that's rather quick.
Can I interrupt for just a second on that note? Because we had a non-prompt group at a value of 0.264, and if you add that to 99.359, you don't get 100. So we're dividing by the total, not necessarily 100.
Okay, wait a minute. Hang on a minute. Ah, wait a minute. This should be 736. Thank you.
Okay, but I guess my question is, given the values that we were on the quiz, we would have divided by that total, not by 100, to get our answer. Is that correct?
For getting L bar, which is the average neutron lifetime, which is considering all the groups, all 7 groups, you would divide by 100. When you go to find the L bar for the delayed group, we're going to have to take this number, subtract this number, and then divide by the total number of betas that are just the delayed group to come up with that value, and I had that value come out to be this. So the delayed group, when you consider all 6, is very lengthy compared to the overall. And again, that allows you to control your reactor because these things are continually being released as the precursors decay after the fission. And I got the same value that you did for the extra credit. When I substituted in values, what I did is I divided both sides by this. cancels out. And then I took the natural log of both sides, and that came out to be when you take the natural log of that, it just becomes this. And then you solve for the reactive period, and that again was minus 11.99 seconds. Okay. So on this exam you'll have coming up for chapter 10, you will be doing another one of these problems. I will give you another fuel, and I will ask you to find the average neutron lifetime and the delayed neutron lifetime. Just to go back to that, any questions on how we calculated those values? If you go back and you look at example 3 on page 304, that shows you exactly how to do it. The only thing that was not well described in the book was the using the 10 to the minus 3 for the prompt group. Any questions on any of that? Okay. We had gone through the effect of delayed neutrons. I showed you that plot about with delayed neutrons, without delayed neutrons. I think what I'd like to do now is develop the equation for a transient reactor. And this starts on page 306. If you have your textbook, you might want to follow me with this. Okay. If we look at a transient reactor, again, we know that the rate of change with the neutrons with respect to time is not equal to 0. And instead of looking at all the possible variables that might impact the neutron population, and in this case, we're saying we're just looking at one of them, which is time, they're saying we're going to make this just be solely a function of time. And to start off, since we like to operate around criticality, we start off and say that that's essentially equal to 0, just for the ease of doing math. Whenever you go to set up an equation, we can always say that this is production minus loss. Okay. And in this particular case, if I look at the production term, there are actually 7 parts to that. We have the prompt neutrons, and then we have delayed group 1, delayed group 2, 3, 4, 5, and 6. For losses, we still have leakage, and we still have absorption. What your book does for the bottom of page 306 through 307 into the top of page 308, they are developing a solution to this. And you're having 7 production terms, 2 losses, and when the dust settles out of this, what you're going to end up with is an equation of reactivity as a function of reactor period. And in particular, it is equation 10.20. And this is a shorthand notation, and they have lumped all of the 6 delayed groups into this. So when you actually go to use this, this is going to become, so I'll just write it down here, so this is called the full in our equation. And when you go back and look at the individual components in this, this relates to just the prompt neutrons. This group accounts for just the beta 1 group, beta 2, beta 3, beta 4, beta 5, beta 6. If I asked you to find the reactivity associated with a particular reactor period, let's say for this uranium 233, I ask you to find the reactivity if we want the stable reactor period to be 3,000 seconds. If you go back and look at the full NR equation, you'll see that reactivity is only a function of reactor period. All the rest of these values are a physical property of the fuel that we're using. So if we go back and do this, okay. If we look at the prompt group, what is the L going to be? The L for any fuel is always going to be 10 to the minus 3 seconds. What is K effective? We always consider we're operating around criticality, so K effective is always going to be 1. We don't do anything in major steps, we do baby steps. What is T? T is going to be whatever the value of period that we want to be. If we then go in, and again, we're using uranium 233, we'd have to go back to the table that was on page 303. And if we look at beta 1 for uranium 233, you'll see that that value is 0.023. Everybody following me on that? But if you look at the table, that is a percentage. It's not a real number. So the number you have to use is you have to add 2 zeros to that to make it a real number. And then we have the
Repeating
remaining.
that part again?
Say that again?
You mind repeating that part again? What do you have to do to make it a real number?
You're going to take the beta 1 value out of, in this case, since we use 233, you'd go back to the table on page 303, table 10.2, and for beta group 1, if you read across, for uranium-233, that number was 0.023. But that is a percentage, it's not a real number. So to make it a real number, we have to put 2 zeros in front of it. So this beta value is 0.00 and then the 0.23.
Do we do that with all of the B values by adding the 2 zeros?
Yes. And so the next thing is lambda 1. And if you remember from before, lambda 1 is equal to 0.693 divided by the half-life of that particular group. So if we go back here, what is lambda 1? If you look at that table, the half-life, and actually it's not on that table, it's on the quiz that you just had. So the half-life for group 1 was, so we're going to go back here, it's going to be 0.693. And what was the half-life? It was 54.84 seconds. So that is lambda 1. Then when you multiply times t, it will make it dimensionless again because the seconds will cancel with seconds.
Professor, when you showed us the example from the quiz we just did, and you did the lambda, you divided the half-life by 0.693, not 0.693 divided by the half-life.
But look at what it is. It's 1 over lambda I is equal to t to 1/2.
Can you repeat that?
If you're looking at page 304,
Yeah, well, I'm talking about the example you gave us when we did you just went over the quiz. For it, you did half-life divided by 0.693. Why are we changing it?
We were trying to find LMI.
if you go back, what is lambda 1? It's a decay constant. The decay constant is 0.693 divided by the half-life. And you need to have a time in the denominator because the reactor period is going to be time, and you need time to cancel time so that that remains dimensionless. Let's go back and do the next one. Okay? If I look at beta 2 for uranium-233, if I go in the book, it is, by the book I mean the table on page 303. I also gave that to you in the quiz. So that beta value is 0.00 0.079. But again, that is a percentage. You need to add 2 zeros in front of it to make that a real number. If you go in and look at lambda 2, that is going to be 0.693 divided by the half-life for that precursor group. And that precursor group was 24.62 seconds. You go through and do the whole group. Let's go ahead and use group 6. What is the beta for group 6? It is 0.009 from your quiz table. It's also in the book. But again, we need to add 2 zeros to this to make it a real number. And then this lambda 6 is going to be 0.693 divided by that precursor half-life, which was 0.24 seconds. If you then go through and everywhere that there is a t, we substitute in the desired value for our reactor period. So this would be 3,000 seconds. Cancel, cancel. 3,000 seconds. Cancel, cancel. Cancel, cancel. You're going to do that for all of these. And when you do the algebra on that, you're going to come up with a value. And that value, I haven't worked all of that out for this particular case, but whatever you get for a value, let's say this is 6 times 10 to the minus 2. So you've taken this, add it to 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 this. That gives you the total reactivity. What are my units? The units are going to be dimensionless because this seconds will cancel with this seconds. These seconds have already canceled. Everything else is a number. So this final answer is in hours. If you then divide this by beta from 1 to 6, and in this case, it's going to be 0.0, excuse me. And again, you can sort of, from our table, it's 0.264. But again, this is percentage. You will need to make that a real number. So you have to add 2 zeros. When you do that, your answer comes out in dollars. So when you talk with a nuclear engineer or you talk with operational people and they talk about reactivity, they're typically talking about an in-hour value, or they're talking about a dollar value. If you took this value and you moved it by 2 decimal points, instead of dollars, you would have it in cents. But most people don't talk about it that way. They talk about it strictly in dollars. You might not realize what you're doing on this. Before I erase this, is everybody following how to use that full in-hour equation? Because you are going to get one of those on your exam coming up.
So just to be clear at the end, when you calculate the in hours, you're dividing it by the sum of all the B's?
Just the delayed group, 1 to 6.
Right. Thank you.
And the
Does
value,
everybody? Yep, question?
yeah, the value of n hours comes from that entire equation, lambda over K effective
That's
multiplied
right.
by T plus, okay. Thank you.
When I ask you to do the n-hour equation, if I ask you to do the full n-hour equation, you're going to have these 7 individual calculations to do, and then you're going to add those up algebraically to come up with that answer. And because it's dimensionless, the units are n-hours. If you remember back to the original definition of n-hours, it's the amount of reactivity necessary to make the reactor period be exactly 1 hour. That was how it was originally defined when this whole engineering field got started. That's how they came up with n-hours. So this is a little bit of a messy calculation to do. The only things you really have to remember are, no matter what the fuel, this L value is always 10 to the minus 3. K effective, you assume you're always working around 1 because you want to keep everything done in small steps. And then when you go to put in the betas, take whatever the percentage is, but you have to add 2 zeros because you need it to be a real number. When you use the lambda is the decay constant, which is 0.693 divided by the half-life of that particular precursor group. And you're just going to do this for each precursor group. And then you're going to have 7 terms that you end up adding together to come up with that answer. Because it's dimensionless, it is in n-hours. If you then divide that by the beta 1 to 6 for that unique fuel, in our case it's 233, make sure it's a real number, not a percentage, then you'll have the answer in dollars. Okay. If you don't have any other questions on that, I'm going to erase that and go forward a little bit. Any questions on that before I erase it? Okay. When you have the NR equation is equal to that expression I gave you, what you have actually solved to get to this point is we have a set of 7 several simultaneous equations. Basically, we have one equation for the prompt neutrons. We have one for the beta 1 group, all the way down through the beta 6 group. And you are solving this set of 7 simultaneous equations. If the reactivity turns out to be positive, you won't really see this in the work that you're doing. But when you solve that 7 set of simultaneous equations, what you'll come out with is one reactor period is positive, 6 reactor periods are negative when you solve that set of 7 simultaneous equations. But since the reactivity is positive, the only one that will count that we will use is the positive value. But that works itself out when you use that full NR equation. If the reactivity is negative, we have 7 minus values for time. And what we do there is we use T with the largest negative value. The other negative ones will die out. It's just like up here, these other negatives will die out. So reactivity is positive, reactor period is positive, and that's what will show up when you solve this. When in reality, you've ended up with 7 solutions, but only one of them is viable. If reactivity is negative, you'll actually solve this and come up with 7 reactor periods, all of which are negative. But what shuffles out of this when you solve it is you'll end up using the one with the largest negative value. You won't notice this the way we're solving these problems, but this is in reality what is happening. Okay. The final thing I think we'll just cover for today is, if you could flip over with your book, if you flip over to page 310, and in particular, I want you to look at figure 10.5. Okay. And that is a plot of reactivity in hours versus reactor period in seconds. Okay. And if you could, it's hard to see it in that view, but there's actually the solution to the full n-hour equation will plot, and it looks something like that. So, again, if you give me a period that you want to obtain, I can tell you what that reactivity will result, or that you have to have this reactivity to make that reactor period be that. And what the engineers have done is they've broken this down into groups. And if you have anything that is, to follow that down, that is T, where this is 10 to the 0. This other guy out here is really, T is 10 to the 3rd seconds, okay? This is one region. That's a second region. And this is the third region. And the reason they've done that is they've said, okay, rather than solve the full n-hour equation, we can use approximations. So, if I look at this group, which is anything going out in that direction beyond T is equal to 10 to the 3rd, which is 1,000 seconds. If you notice, this tells us that the reactivity can be very adequately estimated or used by L bar over T. So if we have anything that we're using where we want the reactor period to be greater than 1,000 seconds, you can go and solve the full n-hour equation to come up with a value for reactivity, or you can use the expression or the equation reactivity is equal to L bar over T. Where does that L bar come from? Anybody? Hopefully
Doing the
somebody.
calculations and removing the prompt neutrons.
This is the
Oh,
value
That's for all 7, sorry, including the prompt neutrons.
That's right. This is the answer that you just had on your quiz, where you found the average neutron lifetime. So in the quiz we just had for uranium-233, that value was 0.0575 seconds. Whatever you have that you want to use for the reactor period, as long as it's greater than 1,000, let's say it was 2,000 seconds. Cancel, cancel. So it's going to be a dimensionless answer, which the answer is in N-hours. If you went to this full N-hour equation, and you did all of that algebra, the number you get here is going to be very close to whatever this number is here. So a lot of times the engineers will use this shortcut to come up with the reactivity needed to make a reactor period be exactly what you're after. If you're between 10 to the 0, and what is 10 raised to the 0 power? That's right, 1 second. So if you're anywhere between 1 second and 1,000 seconds for what you want the reactor period to be, this tells us that we can use the equation reactivity is equal to L over K effective T, which is exactly this part of the full N-hour equation, plus beta L sub D over L sub D plus T. So if you were anywhere in this region and I asked you to find the reactivity required to make the reactor period be exactly something, you can always go and use the full N-hour equation, or you can use this equation as long as it's within that bounds and have a very close answer. So what is, for example, what is L sub D? That's the average value of the delayed neutrons, which you just solved in your last quiz, which was 21.39 seconds. What is beta? Beta is the delayed neutron groups only, because you've already accounted for the problems here. This is going to be 0. Again, you have to make it a real number. And then whatever you want that reactor period is, anywhere between 1 second and 1,000 seconds. If you plug that in here, you're going to come up with a value for reactivity in N-hours again, because everything cancels out. And hopefully it's going to be very close to using the full N-hour equation.
What did beta represent in that equation again?
Say that again?
What was beta in that last equation?
This one, that's the beta for just the delayed neutrons. Because this, when you look at this, this is what? The prompt neutron contribution. They have lumped all of these together into the delayed neutron contribution. When we're out here, this is just a general expression as long as that you can use as long as T is greater than 1,000. You're not really breaking it down into prompt or delayed. If we have our reactor period be less than 1 second, so you're in this region right here, Your book tells us we could use is equal to L over K effective T plus beta. So this is good for any reactor period that is less than 1 second. What is this? This is still the 10 to the minus 3, 1 times whatever your reactor period is that you want to pick. What's beta? Beta is the total lumping of the delayed group. Again, you have to put the 2 zeros in there. When you do the math, this comes out to give you a reactivity in hours. Again, because it's dimensionless. So I could ask you to, if I gave you something, I asked you to find the reactivity necessary to make the reactor period be exactly 0.4 seconds. What would you do? You could come back and use the full n-hour equation, come up with the 7 terms here that you do the math on, and then you add them together. And that is always the true answer because you're using the full n-hour equation. Or you can use this approximation to come up with usually a very close approximation of your answer. Again, it's in n-hours. If you wanted to make it into dollars, you would divide this by the beta for the particular fuel. And again, make sure that's a real number and not a percentage.
So, Professor, the equation that's in the middle that you circled with red, that's to get an exact answer, and the one to the left is to get the approximation?
All of these. This is an approximation if t is greater than 1,000 seconds. This whole thing is an approximation if the reactor period is greater than 1 but less than 1,000 seconds. This is an approximation if t is less than 1 second. Each of these is an approximation for the full n-hour equation here. The full n-hour equation plots like this blue line. So if you plugged in a number for reactor period in the full n-hour equation and you knew what the specific fuel was, you're going to come up with an answer here. That answer, depending on what this, let's say this was 400 seconds. You're going to come up with an answer, and that answer, wherever 400 seconds is, that's that value. This is guaranteed to be true any application because it's the full n-hour equation. But if I said it's going to be 400 seconds, what is an approximate value that you might want to check or use just to get things going? You could use that approximation answer, or that approximation technique for anything between 1 second and 1,000 seconds. Again, 3 approximations. This is always the gold standard because that's the full n-hour equation. One thing I will probably do on your exam is I will give you a mystery fuel. I'll give you the information on it, and I'll ask you to calculate an average neutron lifetime, a delayed neutron lifetime. I'll give you a reactor period, and I'll ask you to calculate the full n-hour equation, and then I'll ask you to use one of the approximation techniques to see how good that approximation technique is. Any questions on what I've done today? Okay. Any questions? Okay. I have a quiz for you on this. So I'm going to send you that quiz momentarily. This quiz will be due before the start of class on Monday. Okay, I just sent you the quiz. I'm going to ask you to open it up. Let me know when you've got it, and I will. You got everybody opened up the quiz? Has anybody opened up the quiz?
Yes, I have a quiz.
I've got
Okay.
the quiz.
Okay, so I'll read it through with you very quickly. Again, we're going to use our uranium-233 fuel, and we've already calculated in the quiz we just turned in today, L bar and LD bar. So I want you to use the full N-hour equation, and I want to know what would the N-hour value be for reactivity if we want our reactor period to be exactly plus 150 seconds. Full N-hour equation. Then I want to know what is that reactivity in dollars. And next, I want you to use one of the approximation techniques from figure 10.5 and calculate the reactivity in hours. That's the quiz for 10 points. And then for extra credit, and this is not for uranium-233, this is just in general. If a precursor produces a neutron during its decay, and the half-life of that precursor was 8.12 seconds, which delayed neutron group would that be in? So it's going to be B1, 2, 3, 4, 5, or 6. I want you to tell me which one and why. Any questions on that quiz? This will be due at the start of class on Monday. Then I'm going to finish lecturing on reactor theory on Monday. I will give you a quiz that will be due on Wednesday. It'll be on the remaining stuff. And I'm going to do the same thing for nuclear material science. We're going to lecture today. I'm going to give you a quiz that'll be due on Monday. I'm going to lecture on Moore's circle on Monday, give you a quiz that'll be due on Wednesday. We'll go over the 2 quiz solutions on Wednesday. No more quizzes after that. I'll use the balance of the day for anything you'd like to review for either exam. And then that following Monday, which is the 13th, in the class period, and I might see how quickly you can get here rather than start at 12:30. If you can get here at 12:15, I'll let you start at 12:15. You'll have the full hour, but you're going to have 2 exams to do. That'll be due by 3:15 or maybe 3:30 if I talk Professor Lanson to let me slide in his. And again, I will grade them before I leave here. And then I will post your advanced grade with whatever you've done for extra credit, if you turn in a notebook, etc. And then you're going to let me know if you want to do a final exam. Okay? Any questions on this particular quiz? Or anything we did today on reactor theory? Okay. If not, why don't you take a 10-minute break, and I'll see you about 10 of 2. And I'll be looking to see if anybody wants to put the nuclear material science, their quiz solution up on the board. Is anybody interested in doing that? So I guess I'll do mine again. I'll let you think about it. I'll see you at 10 of, and we'll do nuclear material science for the rest of the time. See you then. Okay, the break is just about over. Do I have anybody that would like to put their solution up for extra credit? No takers again, Don? Okay, we're missing one person. The next two exams are going to be on Monday, December 13th, so a week from this Monday. So after lecture today, we'll have lecture on Monday. Then on Wednesday of next week, we will have a little bit of lecture where we review the final two quizzes that are coming in. And then I'll do any review you want to do for either exam. And then the two exams will be given to you simultaneously on Monday, the 13th. I'm going to try to get them to you a little earlier, so if I can get everybody here at 12:15, we'll start at 12:15. If we can start a little earlier, I'll even do that. And you have the full class period to do both exams, and both of them will be turned in that day. I will grade them, and then I will send out later that day an email with what everyone's advanced or your draft grade. And then you have the option of, do you want to do a final exam or not? Okay. When I send out that listing, what you're going to see on one side of the page is you're going to see a number, and that number is going to be the last four digits of your Social Security number. So let's say your last four digits are 0231. Okay. You know who you are, nobody else knows who you are. And then if you go across, you're going to have reactive theory, nuclear material science, and then nuclear material science lab. And so when I send this thing out, and this is going to be in ascending order, so we might start off with 0116, and it might end up down here with 9827. It's going to be descending order. You'll know who you are, and then I'll have a grade in here. And that'll include all your quizzes, all your exams, anything for extra credit that you've done, your notebook. This is your draft grade. I'll send it out Monday, and I'll ask you to get back to me, and I'll probably pick something like Tuesday noon to let me know if you want to take a final exam in either or both. And if you do, I'll probably use Wednesday if you want to review for the ultimate final, or we could have the exams on either Wednesday, Thursday, or Friday, but I have to have grades in by the close of business Friday. So if you opt for a final exam, it'll be from day one of the course through this coming Wednesday. It's a comprehensive exam. Okay. And then all the labs will be due on Thursday, 2 weeks from tomorrow. And then I will send out this grade. It'll be on the same form, but I will send that out probably late on Friday. So there'll be another grade out here. And that will include the 5 written labs that you submitted, plus extra credit for attending the optional one, plus potential extra credit if you wrote that one up. Okay. The other thing I do, because you can't really see this, if you were, I used to post this on my door, but anyway, out of all 24 of you, let's say 7721 had the highest grade for reactive theory. What I used to do when I put it on my door is you got the famous red A. But you can't really see that when I send out an email, so I make this a script A. So I'll denote who the highest one was for each of these courses. Usually, since people tend to work in teams for the labs, I don't really do that because a lot of people end up with the same grades. Okay. We still didn't have anybody who wanted to put the quiz up, right? Okay, so we're going to use mine. What I'll probably do on Monday is I will have this sheet made up with your last 4 digits of your social security number, and I'll just send it out to you so you can see it and make sure you can identify who you are, that I haven't made any mistakes in the numbers. Okay. So,
Professor, the camera is very out of focus. I don't know if maybe there's something on the table by the camera.
nothing is, and it's moved since we had the break.
For whatever, it hasn't moved, but for whatever reason, it's out of focus.
Let me see if I can shut it off and try to get it back again. Is that any better?
Yeah, that's lovely. Thank you.
Is that lovely sarcastic or is that lovely for real?
That's lovely for real.
Okay. All right, so we have our cantilever beam. At the end, acting up from the bottom, we have a 10,000 Newton force. If we look at the cross section of this, this is our same old friend that we've had for quite a while now. And I did that so you wouldn't necessarily have to go back and redo all those calculations again. Because I know you're getting expert at that now, so there's no need to have you redo that. So from this, we know that the neutral axis was at 6.04 centimeters. And we knew the rectangular moment of inertia for this particular cross section was 1,368. That's unique to this orientation. So the first thing I asked you to do was to draw a complete free body diagram, but to also label tension and compression areas. So if this is pushing up, this is going to distort upwards like that. So the bottom is going to be in tension. The top is going to be in compression. And we can look at it in this view, but it's the same thing holds over here. The bottom is in tension. The top is in compression. Okay. I then ask you to draw a complete free body diagram. So again, we sketch the member. Join any given forces, moments, torques, couples. You have our 10,000 newtons there. We have one attachment point at the wall, and we know we can only add for equilibrium forces, moments, torques, couples at the attachment point. We look at our 6 equilibrium equations. We only have something going in the y direction, so that one doesn't do anything, that one doesn't do anything. And for the f of y, again, we know that it has to be 0 and that the ups have to equal the downs. So that guy's acting up. So the down has to be that amount. And again, I could show it up here. I could likewise show it down here, because this is the same as this, because it's acting along the same line of action. So we'll keep it up there. Is that a complete free body diagram? No, because if you look at this, what's going to happen? With this force acting up, this one acting down, this thing will want to spin or rotate counterclockwise. So now we have to look at the moments for equilibrium. What's happening about the x-axis? What's happening about the y-axis? What's happening about the z-axis? And again, if it's going to rotate this way counterclockwise, that's around the z-axis. So those don't make any difference. We know the sum of moments around the z-axis has to exactly equal 0, or the clockwise have to equal the counterclockwise. We can take the moment wherever we choose, but typically the best place to take it is if you're going to apply the moment here, and again, you can only apply the moment at the attachment point. We could call that point, let's call it P. So we'll take the moments around the z-axis at point P. We know the clockwises have to equal the counterclockwise. Put our finger here. This one does nothing because the lever arm is 0. If we look at this guy, its line of action is up like this. So that is the perpendicular distance to that. And that's making it want to go counterclockwise. So it is 10,000 newtons times that distance, which is 8 meters. So that is 80,000 newton meters. And that's going counterclockwise. So in order to be in equilibrium, we have to apply one in a clockwise direction, exactly equal to that. So this is a complete free body diagram for that cantilever beam. Any questions so far? Okay. I'm going to erase this. And one of the things we're always interested in is safety. And when we look at safety, we're always concerned with plane stress, and we're interested in shear stress. Probably the easier one to do here is shear stress. And shear stress is equal to shear force divided by the area that's parallel to it. So if we look at this member, wherever we might cut it, and we look at a section, let's just look at this section. Let's look at the left-hand side. We have 10,000 newtons acting down. This is our attachment point. So we have to have 10,000 newtons acting up. So no matter where we cut this, we're still going to get this same version where this guy has to be acting up. So the shearing force is uniform anywhere along that length. It's actually equal to 10,000 newtons. If I went back and looked at the area that was parallel, and again, that was our shape. If we calculated that total area from the earlier problem, that was 67.3 times 10 to the minus 4th meters squared. When I did this math, that value came out to be 1.49 megapascals. I want to compare this to the yield value for my aluminum 1100, and the yield value was 55 megapascals. This is less than this. So at least for this guy, it's safe. And no matter where I cut it, we're going to get the same shear stress. Any questions on what we've done so far? Okay? Let's go and look at plane stress. We know plane stress is either equal to an axial force divided by the area perpendicular to it, or it's equal to a force that the moment creates a plane stress. If we want to find the maximum value, we need to look at the maximum value for our moment. We also need to look at the maximum value for our y value. And going back to our free body diagram, and looking at this, since the bottom is in tension and the top is in compression, if I look at this very bottom point right here where it attaches to the wall, that's going to be my maximum value for plane stress, but it's going to be tension. If I go to the top where it's attached to the wall, that's going to be my maximum value for compression. You then have to say, is the maximum value for tension equal to, greater than, or less than the maximum value for compression? How do we do that? We have to look at y, which is the distance from the neutral axis to the point of interest. So in this case, this bottom point is the maximum value for tensile plane stress, and that value was 6.04. So down here in this view is going to be sigma max tension. We look at the top of our little triangle, that's going to be sigma max compression. So we need to know how far this guy is away from our neutral axis. This whole thing is 5 plus 6 plus 4, which is 15. So if this total is 15, and this is 6.04, this part has to be 8.96. So the thing we're concerned about with safety is going to be the maximum value, and the maximum value for plane stress is going to be at the top for compression. We're not worried about this one because there is no axial force. If we look at this one, what is the moment? Since it's at the wall, we already have that value. It is 80,000 Newton meters. What is my y value? Y is the distance from the neutral axis to the point in question, which was 8.96 times 10 to the minus 2 meters. What is my I value? That was from the original problem, which was 1386 times 10 to the minus 4th meters to the 4th. When I did the algebra on that, I had that value come out to be 524 megapascals, but it is compressive. So this is minus 524 megapascals. I then go back and say, what is the yield value for my aluminum 1100? And that was 95 megapascals. So this is going to fail, and fail big time. So as it starts to fail, and we know it's going to fail, where is it going to fail first? It's going to fail where this is the largest value reached first, which is going to be here. So when it starts to fail, the first point is going to be right there. But eventually it's going to fail all the way along the attachment, and it'll just break off at the wall. Um, Any questions on what we've done so far? Everybody feeling comfortable with that? Okay? Let me erase the top and over there. Okay, let me go back to my original free body diagram. And now I've asked you for point A. And point A in this view is right here. Point A in this view is 1.2 meters from the end. So point A, you would see it here in this view, it'd be there in that view, and I wanted to know what is the plane stress at point A. So we know the equation for plane stress, if it involves a moment, is my over I. I, remember, is a physical property of the cross-section, so that's going to have that same value of okay. Now, what is the moment at point A, and what is the Y value at point A? Let's look at the moment first. How are we going to do that? We need to do a free body diagram. So let's go exactly 1.2 meters from the end. Excuse me. If we're going to cut that, we could do a free body diagram of the left-hand side, but it looks like it might be a little easier to do one from the right-hand side. Doesn't make any difference which way you go because you're going to come up with the same answer. The only difference is if you do it one way, you'll come up with an answer. If you do it the other way, it's going to be exactly the opposite. So when you put the two back together, they cancel one another out. So let's do the right-hand side. Okay. And this distance was 1.2 meters. So we've sketched the right-hand side. You draw on, again, any given forces, moments, torques, couples you have. 10,000 newtons. To complete your free body diagram, you know that this guy has to be acting down. Okay. Again, this makes it want to go counterclockwise, so we know we're going to have a moment here going this direction. If we put our finger in the cut, this one creates no moment, but this one, perpendicular distance, it's going to be 10,000 newtons times 1.2 meters. That is its moment, so that'll be 12,000 newton meters. So I can go back here, this value is 12,000 newton meters. Okay. This is point A. This point is 5 centimeters up from the baseline. My neutral axis was at 6.04, and Y is defined as the distance from the neutral axis to the point of interest. So I'm interested in this distance, and that's going to be taking advantage of the baseline, 6.04 minus 5 times 10 to the minus 2 meters. When I did my algebra on that, I had that guy come out to be 9.12 megapascals. And is the sign going to be positive or negative? We know the bottom is in tension. Anything below the neutral axis is in tension. Point A is below the neutral axis. So that is my value. Any questions on the quiz? Everybody think they're getting the hang of cantilever beams. It's sort of the same old thing. It's drawing a free body diagram. and then looking to see what you have. Let's look at a little variation of this. No questions, no problems on this, right? So I'm going to erase this and draw it back in here. Okay. Let me take a slightly different version of this. Okay, and we have our same cross section. And now let's try something a little different. Let's try this time, but I also add a force acting in that direction of 6,000 newtons. And I'm going to ask you again to draw a complete free body diagram, and then I'm going to ask you to look at safety. All right. First thing we're going to do is our free body diagram. Sketch, remember, drawing any given forces, moments, torques, couples. We still have one attachment point. So that attachment point is the only place we can add forces, moments, torques, couples to put in equilibrium. And the only way we do that is look at our 6 equilibrium equations. We look at sum of forces in the x direction, sum of forces in the y direction, sum of forces in the z direction. Okay. Now we know that the lefts have to equal the rights. But this guy is going in that direction for 6,000. So that's going left. So this guy has to go right, and it has to also equal 6,000. So this member, this cantilever, is also in compression. If we look at forces in the y, yes, we do. The ups have to equal the downs. And just like before, this has to be that way. There's nothing for forces coming in and out of the board, so this guy doesn't count. It's 0. That isn't complete, because if you look at this, this sort of cancels other out, but this still makes it want to go counterclockwise. So we're going to have to look at sum of moments around each axis. And now for equilibrium, they have to exactly equal 0. There's nothing making it rotate around the x-axis. There's nothing making it want to rotate around the y-axis. But there is something about the z-axis, and again, I would typically recommend you pick the point for the attachment point. So again, we'll call that point P, and you know the clockwises have to equal the counterclockwise. If we put our finger here, this force does nothing, this force does nothing, this force does nothing, because again, they go through your finger with no lever arm. This is still the 10,000 times the 8 meters. So this value is still going to be 80,000 Newton meters. This is a complete free body diagram. If we then go back to look at safety, and again, if we look at shear stress, we know that's equal to shear force divided by the area parallel to it. And again, anywhere you cut this vertically, this is going to be my 10,000 newtons divided by that area, which was, excuse me, 67.3 times 10 to the minus 4 meters squared. And we compare that value to the yield value. If you do that, nothing has changed from before. But if we go back and look at plane stress, if you remember, plane stress can be found one of two ways. It's either an axial force divided by an area perpendicular that it's acting across, or it's also equal to a moment times y over I if a moment is involved. So in this case, what happens? We have two different contributions. So if I pick a point, and let's go back and pick, since this was our maximum value before, we know this was the maximum value for compression. Yeah? Because when we did this, the bottom was in tension, top was in tension, compression. So this value was the maximum value for compression. We found that before. But if we call this a new point, let's call that point J in my honor. Okay? What do we have? We have a plane stress that is caused by this axial force divided by the area that's perpendicular to it. What is that axial force? At this point, it is 6,000 newtons. What is that area? That area is that same area as here. Okay. But it is also compressive. So that value is minus. If we then go back and look at what is caused by our moment, that is going to be the exact same value that we had to start with before, which was our 80,000 Newton meters. The distance from our neutral axis up to there was 15 minus 6.04, that's 7 minus 2 meters. And our I value was 1368 times 10 to the minus 8 meters to the fourth. This turned out to be minus 524 megapascals. I didn't calculate that, but we could do that very quickly for the other one. So that is 6,000 divided by 67.3 equals 89.15. Move that up times 10 to the fourth, but we need it in megapascals, so we'd move it over here. So this part is 0.89 megapascals. It is compressive, so it is minus. So the total plane stress at point J is this plus this. This is a value that you'd compare to safety against the yield value. It failed before, and now it's even more negative, so it's going to still fail. So we could pick anywhere. So if we go back, since we've already done a bunch of calculations for A, let's go back and find what is, and I'm going to erase this. What is the plane stress at point A? We know it's the axial force, because we do have an axial force in this case, divided by the area. What is that axial force? It was 6,000 newtons divided by our area, which was 67.3 times 10 to the minus fourth meters squared. And that's still going to be my 0.89 megapascals. Anything in this entire beam is in compression. So that guy is minus. If I then go and look at the moment part, that's going to be the same calculation that I did before, where, remember, we cut it here, we looked at the moment that was acting here, and that value was, this was 12,000 Newton meters. That distance was 6.04 minus 5, 10 to the minus 2 meters. And my I value was still 1368 times 10 to the minus 8 meters a fourth. And that value that we calculated before was plus 9.12 megapascals. So if I add this and this, that value is plus 8.23 megapascals is the plane stress at point A. So we can find the stresses, the strains, anything we want to anywhere in our system. If you want to pick a different point, let's pick let's call that point B. And if we go back to our original drawing, let's say that this point B is 4.2 meters from the end. Okay? And I want to find out what is the plane stress at point B. What is the shear stress at point B? It is still the shearing force divided by the area. So it has this value anywhere in here. But let's go back and look at the plane stress. Again, plane stress at B, we have part that is caused by the axial force. So that is still that value. And that value is still minus 0.89 megapascals. That is a uniform stress throughout the system. We then go to look at what's the contribution due to the bending. My I is still going to be the same value. What is Y? Y is the distance from the neutral axis to the point of interest. So again, from my baseline, Y is going to be, if we go all the way up, it's going to be 5 plus 6, which is 11. And then if we go to just the neutral axis, that was 6.04. So that distance is 11 minus 6.04, again, times 10 to the minus 2 meters. Now we need the moment that exists there. How do we do that? We go back to our initial free body diagram, and we now cut this. We could cut it exactly at the point of interest. And again, we could look at the left-hand side, or we could look at the right-hand side. In this case, I'm still going to do the right-hand side. So we'll draw the free body diagram for that. We sketch, remember, now we go on any given forces, moments, torques, couples. We have one attachment point. Equilibrium equation, sum of forces in the x direction. So this guy has to be this. No surprises there because we know it's in compression. This guy is going this way. Again, no surprises, because we know it's a uniform shear all the way along. So what is the moment? These two cancel out. This one and this one makes it want to go counterclockwise, so we're going to need to add a moment going in that direction. What is that value going to be? That distance is 4.2. So again, if we put our finger here, this force, this force, this force have no bearing on creating a moment because they go back line of action through my finger. It's only this guy. So my moment is 10,000 newtons times the distance, which is 4.2 meters. So this value is going to be 42,000 Newton meters. And again, it has to be going clockwise to keep the system in equilibrium. When we look at this, we're going to come up with this times this times this, whatever that number is. Then we need to see whether it's going to be a plus or minus. Point B is above the neutral axis. Everything above the neutral axis is in compression. So whenever you do this calculation, this contribution is going to be negative. And then when you go to find the total at B, it's going to be that part, which is minus 0.89. And then whatever this is, which is going to be minus, we could do that real quick if you want to. I got that to be 152.28. Negative and negative, so it's going to be minus adding those two together. 153.17 megapascals is the plane stress at point B. Any questions on that?
Yeah, so if we wanted to calculate that using the left-hand side,
Yes?
how would that happen?
Okay. So what I'm going to do, I'm going to go back and I'm going to still cut this at there, okay? So I sketched the member as given. We're now looking at the left-hand side. I draw in any given forces, moments, torques, couples. So what do we have? So I'm now looking at this. We've cut it here. And I'm looking at this left-hand side. So what do we have? Well, actually, I didn't draw this complete up here, so this would have to be this is what, 80,000. Okay. So we draw on any given forces, moments, torques, couples. So this is 6,000. Like the sum of forces. Well, let me draw on the givens here first. Okay. We have one attachment point. We can only add forces, moments, torques, couples to do that. So we have to have this guy because we know it's in compression. This guy has to act up. Okay. Now what do we do? Okay. We look at this point, and this point was B. Okay. And we want to see what we need for a moment there. If we put our finger here, this force, and this force do nothing. We put our finger here and we look at this force, this makes it want to go counterclockwise. And that counterclockwise amount is 10,000 times that straight line distance. And what is that straight line distance? If this is 4.2 and this whole thing was 8 meters, that's going to be 3.8. And that's going to make it want to go counterclockwise. But we also have this down here, which is 80,000 going clockwise. So this is going to be 38,000 meters, and this is going to be 80,000 meters. So what we need is counterclockwise of the difference between the two, which would be 42,000 Newton meters. Ah, what do we have for the other way?
Right.
42,000
Yeah,
Newton meters.
got it. Thank you.
Whenever you do a free body diagram, remember the beauty of doing free body diagrams is we did it just looking at the right-hand side, and we came up with values at the attachment point. We just did it looking at the left-hand side, and we got values at the attachment point. The beauty is you can do it either way. You're still going to come up with the same numbers, but you always have a checks and balance, because if you take the left-hand side, take the right-hand side, and you join them back together to create your original cantilever beam, this cancels with this cancels with that, and this cancels with that. It cancels out. If it doesn't cancel out, you've made a math mistake somewhere. That's the beauty of free body diagrams and using the 6 equilibrium equations. In this case, I picked the right-hand side because to me it was a little simpler. It was easier to calculate. But as I think you can see, you can do it from the other side. If you've got yourself in a mindset now that you're always going to take forces, moments, whatever, starting at the wall and working out, that's great. You know it's going to work. But if you have a technique that maybe will shorten a little your math, have less opportunity to screw something up, take advantage of it. Any questions about what we've done here? Okay. Next thing we're going to do is take a look and cut our number a different way. So I'm going to erase all this. I'm going to keep this. I'll erase these points. Okay. I'm going to go back and I'm going to sketch in my free body diagram. And we've already done this before. And I'm going to do it for the one we originally had, which just had this guy, this guy, our attachment point, and again, just to be precise, we know that the bottom was in tension, the top was in compression. Okay. When we look at this, if we look at this in real time, or if we look at it in this view, we have a triangle on top of a rectangle on top of a semicircle. And if I extend these lines over, in other words, if I take it in this view and turn it 90 degrees, so you're looking at it sideways, you will see a line here that represents a discontinuity between where the triangle joins a rectangle or where the rectangle joins the semicircle. If you've ever had graphics before, that's how you show that type of thing. Okay? So, doesn't impact anything we've done for the free body diagram. But up till now, anytime we've used information to find out what's going on with a stress or a strain, we've looked at cutting this vertically. Could we cut this horizontally? And the answer is yes. Let's say we cut it right here. So we're going to do a horizontal cut. Okay. So if I come over here, I'm going to cut it right along here. I'm cutting it here, right where the semicircle joins the rectangle. I'm showing it here. Here, that would show up here. So I'm cutting it, and I'm actually cutting a plane. Okay. I could then look at this and say, could I draw a free body diagram of the upper half of this? And then conversely, could I draw a free body diagram of the lower half? And the answer is absolutely. You can draw a free body diagram whenever you want to. And you know, if you use the equilibrium equations, we can make that stand up. Okay. Let's say we draw it of the upper half. So what we're going to have is, should actually make this a wavy line to show that we've cut it. So I've cut it right here. This just delineates the triangle above and then the rectangle. So when I do that, I have the upper half. In this case, when I cut it, I have one attachment point. So I know whatever I have to put in for forces, moments, torques, couples, I can only add at that attachment point. So when we do the free body diagram, what do? We put in whatever we have for forces, moments, torques, couples. Okay. Now, what I like to do in this particular case is take this 80,000 Newton meter moment and convert it into a plane stress. And if you remember, plane stress is equal to my over I. And we calculated back for the quiz a maximum value for compression. And I think I got to remember if we did it or if I did it. We can also calculate a maximum value for tension. Okay. We know the maximum value for compression, since compression's on the top, is going to be right here. Likewise, at the bottom, tension. Okay. We know that the plane stress is exactly 0 on the neutral axis. So if I sketch the neutral axis in here, and again, it's this same neutral axis here. Because remember, the neutral axis is really a neutral plane. Okay? We know that everything above on the neutral axis, the stress is exactly 0. As we leave the neutral axis and we go to the upper member, this value increases because y is increasing. So at exactly where y is equal to 0, if this is 0, there is no stress. As we go up, this varies linearly. So this is a plot of sigma, and in particular, this is compressive. Okay? So we know compressive tends to go back like this. So I could take away my moment and now make a free body diagram of forces versus stresses rather than forces versus moment. Therefore, down here, this would go down to sigma max tension. This would go up here, sigma max compression. And in this case, this would have to go in this direction to denote plus. So if I found out what this value was, and we know this value from before was 524 megapascals. Just for argument's sake right now, maybe I should do that very quickly. So I had this value be 353.22 megapascals. Okay. So I've cut it. I converted it from a force moment free body diagram to a force stress free body diagram. When you do this, hopefully you can see that this force and this force still want to make it rotate counterclockwise. So we need something to make it want to go clockwise. The only thing we can really add here is a force, and we have to add a force. We call this H for horizontal shear versus this, which is a vertical shear. So we have to be able to calculate a value for that. And we also have to pick a direction. So we know that this force and this force make it want to go counterclockwise. So we need this whole thing to make it want to go clockwise. The majority of this is going in that direction. So we would need the force for horizontal shear to go in that direction to make this thing want to counterbalance itself with a clockwise moment. Your book did some calculations for you, and they showed you how to develop that value. Heather, did you have a question? Oh, there's somebody in the hallway. Excuse me a minute. Your book has developed an expression for this, and as it turns out, H is equal to FQX divided by I. I is the rectangular moment of inertia for this entire shape, and that was 1368 times 10 to the minus 8th meters to the fourth. What was our force? Our force was that vertical force.
Do you have a reference page for where that equation is in the book?
I didn't bring that book with me. I'll try to find it and I'll email it out to you later.
Okay, thank you.
This force is this vertical shearing force, so that is 10,000 newtons. X is the length of this cut, which is 8 meters. And that just leaves Q. And Q is equal to the area involved that you're cutting off times the centroid of that area from the neutral axis. So when we do this, there are two ways that we can do this. There's the easier way, and then there's the more difficult way. Because again, no matter which way you calculate it, it's still going to come out the same. So what is the area? The way we've cut it, if we're looking at the upper half, if we've cut it right here, the area for the upper half is all of that. So for the upper half, it is equal to the rectangle plus the triangle. And we add those two together, and that is the area. What is Y bar? Y bar is a distance from the neutral axis to the centroid of this shape. Do we know what that is right now? No. So Y bar is equal to the distance from the neutral axis to the centroid of the shape cut off. So could we find that? Sure. We'd need to do a little neutral axis calculation for just this upper area, where this is the baseline now. So that area would be 2 times 6. Half of 6 is 3, plus the triangle, area is 1/2 times 6 times 4. And its centroid is 6 plus h over 3. H here was 4. So this is the neutral axis, or this is neutral axis is what? It's the centroid of the shape. So we're going to find a centroid, and let's say that centroid is right there. So this tells us we need the distance from the neutral axis to the centroid of the shape. So this is the neutral axis before. So we're after that distance that you plug into here. When you plug that back into here and you do all the math, this is going to come out to be a horizontal force. So the answer will be in newtons, and that'll be that value. If you did it looking at the other direction, and I could have done the same thing, a free body diagram looking at the lower half. So let me go up here and erase this. And we're now going to look at the lower half. Okay. So this is my cut line. I have my one attachment point. So I have 10,000 here. I still have to have 10,000 there. I converted this from a moment to a stress. So this is my cut line, which is below the neutral axis. So in this case, this is going to come down like this, and then go down like this. So again, when you do the clockwise versus the other, this is going to have to end up going in the other direction, because we know if we put them back together, it balances out. When you go to calculate this H from this view, F is still the same, because that's the vertical cut force. X is still the same because it's the length of the cut. I is still the same because it's the rectangular moment of inertia of that entire cross-sectional shape. What is Q? Q is still area times Y bar, but what is the area this time? The area this time is only the area of the semicircle. You can go immediately in the back of the book and find out where that centroid is. So what we're interested in is the distance from the neutral axis to the centroid of that shape that got cut off. And lo and behold, when you do it this way, you're going to get the exact same value for Q that you do for this way. And when you plug it back in here, you're going to get the same but equal and opposite value for H.
Can we talk about the forces on the left-hand side where we changed the 80,000 Newton meters into the compression and tension formula? Yes.
Yep.
So the neutral axis is going to be above that cut line.
Yes. So let me erase this. Let me go back and resketch this whole thing. This is 5 centimeters up where I cut it. This is my cut line. We know the top is in compression. We know the bottom is in tension. We know that the neutral axis is exactly where the plane stress is exactly equal to 0. And we know it varies linearly by that equation. So the plane stress is linear related to the distance from the neutral axis. So if my neutral axis is here and everything above is compression, it is a linear straight line like this, because we know the stress here is 0. This is the maximum value up here. Since it is compressive, this has to go in that direction. We know the maximum value for tension is on the bottom. And we know that it also varies linearly from Y. So it's going to go in this direction linearly, where this is the maximum value. It's in tension, so this has to go like that. So if I had a complete free body diagram, I would have this at 10,000, this at 10,000, and then I replace my moment with plane stresses. So this is a free body diagram with forces and stresses. The other one was a free body diagram with forces and a moment. If I then go to make my cut, and I made it here exactly where the semicircle was, if this is my cut line, and I go and do the upper half, and I go to calculate H, if I sketch what that looks like, since this and this make it want to go counterclockwise, we need a horizontal shear when compared with these stresses that makes it want to go clockwise. So this is going to have to be going in that direction. And we know the equation is where this is the vertical force applied, Q is equal to the area times its y bar, X is equal to the length of the cut, and I is equal to the rectangular moment of inertia for that cross section. Okay, when we did all these calculations, we came up with a value for H. Let's say that value for H, I'm just going to invent something right now. Let's say this was 8,000 newtons. Okay? So this is a horizontal shearing force, and we know how to calculate it. Suppose I ask you, is this system going to fail along this horizontal cut? The only thing you can do to decide that is you need to find a shear stress that's acting in this cut. And how do you do that? You would divide this horizontal force by the area that's parallel to it. What is that area that's parallel to it? This cut is 8 meters long, and this cut here was 2 centimeters. Now you'd have to get like units here, so we need to make this into meters, so this would be 2 times 10 to the minus 2 meters, because we need to have newtons per square meter. So if we divided this force by, if you would, it's the area of this cut plane. You see it here like this, over here, you see it like this. So it's actually a rectangular plane that's 2 centimeters by 8 centimeters long. And if we divide the force by that, we have the horizontal shearing force. We could compare that to the yield value and see if that material would fail at that cut. Okay.
Okay. I'm sorry to keep asking questions. I'm not sure where the 2 centimeter came from.
We look at the rectangle, okay? What is the dimensions of the rectangle? It is 6
No, I see
centimeters.
it now. Yeah. I hadn't rotated it 90 degrees in my head, but now I see.
So what you have to do is you're looking at a plane that is 2 centimeters by 8 meters. So this force is acting parallel to that, and that's how you convert the force to a horizontal shearing stress. And then you could compare that to the yield value to see if that was going to fail along that line. Okay? Any other questions? I do have a quiz on this I'm going to give you. On Monday.
When you made the cut for the lower section, the lower half, when we were looking at that, that would only be in tension, since the neutral axis would be above the cut line? Or is that not correct?
Meaning this value? That's not, the shear stress is not really tension or compression. It's shearing.
Right, but when you just drew the free body diagram for the lower half,
Okay.
in the previous,
Let me go back up and do the lower half,
okay,
because I don't have the lower up here anymore. So I'm just going to erase this. Okay. So 10,000 is good. Got to put another 10,000 here. And then if that was the cut line, it already has a negative value on that cut line because it's below the neutral axis. So this is going in the direction because it's in tension. Okay. And in this case, we have this, it makes it want to go that way. So here we'd have to have the horizontal shear going that direction, so it makes it want to go clockwise. Just like the one down here was primarily that way, they're going to balance one another out. So it doesn't make any difference when you made this cut. If you're calculating horizontal shear, you could do it looking at the upper half, or you could do it looking at the lower half. You're going to get the same numerical answer for shearing force. You just have to realize whether it's going in that direction or going in that direction because of the free body diagram and equilibrium.
Okay, thank you. It was I guess I misinterpreted the picture that you drew originally because I thought you also had a linear line going in a compressive direction as well. So I see it's all.
Well, in this particular case, it's all going in that way. But if we go back to the upper part, there was a little section here that was tensile from where we cut it. Because remember, this is the cut line, but this is the neutral axis. So everything above the neutral axis was in compression. Everything below was in tension. But we had a little bit of distance here where we had positive plane stress. And this is our cut line.
Okay, I see that now. Thank you.
Okay, I do have a quiz for you, so let me give you the quiz real quick. Okay, I just sent you the quiz. Okay, let me know when you got it. You opened it up, and I'll read it with you and go over it with you very quickly.
We got it.
Okay, so we're going back to the same cantilever beam that you just had on the last quiz. So the cross-sectional area is the same. The neutral axis is the same. The tension and compression areas. The vertical shear forces. This time, instead of cutting this here, I want you to cut it here where the triangle joins that. And I want you to sketch for me a free body diagram of the upper half. And then I want you to calculate the shearing force H that occurs when you did that. That's part A. Then as a check and balance, I want you to do a complete free body diagram for the lower half of this, and then calculate H looking at that part. And as I told you, when you get through, if you use the upper half or you use the lower half, you're still going to come up with the numerical same value for H, so you know you did it correctly. The only difference is one time it'll be going in one direction, the other time it'll be going in the other direction, because you know when you put the two pieces back together for equilibrium, they have to cancel out. Okay. That's worth 10 points. And then for extra credit, I want you to tell me, where does the horizontal shear force have its maximum value? That's worth 2 points. Okay. For those of you that are going to URI tomorrow, I will bring with you your exams from nuclear material science. I will also have graded the 2 quizzes that you turned in today. I'll give you everything back in person tomorrow. For those of you that went on Tuesday, I will have your quizzes graded and I will give them to, you guys have electrical lab tomorrow morning?
On Friday.
I'm sorry, Friday morning, yes?
Yes.
Okay, I will give those other 2 sets of quizzes to the people that had the lab yesterday. I'll give it to somebody that has the 8 o'clock lab for electrical, and they can put them in the box next to security. I will be in on Friday. I'm having lunch with one of the people on my advisory committee. He just stepped down. He was the Commodore for Squadron 4 at the subbase. He had 16 submarines home ported here that were under him directly. He just got transferred. He's now the director of their artificial intelligence research area. He and I get together fairly often for lunch, so we're having lunch on Friday. And I will be into the college after that. I'll probably get in about 12:30 or 1. I know a lot of you are thinking about continuing your education and or looking for a job. If anybody is interested in joining the Navy has a program. It used to be called NESEP. I'm not exactly sure of the new title, but you can apply for that. And if you get accepted, they will send you off at their full expense to a university to get your degree. It's usually in nuclear engineering or health physics. And they tend to send a lot of people out to Oregon State in Corvallis, Oregon. They pay for everything. You get your baccalaureate degree. When you obtain your baccalaureate degree, you're then commissioned as an ensign in the Navy, but you do have obligated time, and it's usually 2 for 1. So if you go for 2 years, then you owe them 4 years of service. But if you're looking for a job, you're looking for to get your degree, we do have people on occasion that have done that. If anybody's interested, he is a guy I would direct you to talk about that going forward. Don't want to keep you too much longer because I know you got Professor Lance today. One other thing, just in passing, when I went down due to the break, I got an email from the accounting office that they have not sent out the paperwork to Hartford for the December stipend checks yet because they have found that Hartford posted some tuition and fees incorrectly. So they've had to go back and get all of that squared away because I cannot spend more than the amount of money that they send me. They hopefully will have that done before they leave today. I will approve it, and then hopefully the checks will be processed tomorrow in Hartford. If not, it might have to wait till Friday. But we're on the tail end of that dog. We have to trust that they have posted the amounts for like tuition and fees and that type of thing correctly, which apparently they didn't do. And I am closing out the spreadsheet on this for this semester with these checks. I will be around today to my usual 6 or 7 o'clock working on stuff. And I'll see half of you at URI tomorrow. And again, if you want to see me on Friday, I will probably get in 12:30 to 1 o'clock if you want to see me on Friday. Otherwise, see half of you tomorrow. I'll see everybody next Monday. Take care.